Hey guys, so we are back, and you're going to get some instruction on Lewis structures. So you guys will get Chem Quest number 21 from me here tomorrow, and we're going to start delving into some molecular model kits, looking at the three-dimensional shape of some of these structures as well. All right. So first of all, the central, big idea of this unit is chemical bonds. We're going to focus probably mostly on our covalent bonds for what we're doing, but I do want to make sure we understand that a chemical bond is a lasting attraction between atoms, right, or ions in some cases. And so they form this attraction and they essentially stick together to form compounds. All right. If it's an electrostatic attraction, it's an ionic bond. If they're sharing electrons, we call it a covalent bond. And, we've already differentiated between a polar and nonpolar covalent bonds. All right. But the thing they have in common is all bonds involve electrons. All right. And if we run a chemical reaction, for example, right, we're essentially just following electrons. We're breaking bonds and then forming bonds between something else to make new materials, right? That is a chemical reaction, right? But the bond breaking and bond forming is just electrons moving around, essentially. Okay? So that's what we mean when we say chemical bonds. Two or more atoms or ions that essentially stick together through either electrostatic forces or through the sharing of electrons. All right. So we have what we're called Lewis structures. These are not the same thing with Lewis dot structures, although the underlying skill for these Lewis dot structures is important, because you'll notice we do still have the dots. Okay, but we're also showing the location of bonds, right? So Lewis structures are a method for modeling the arrangement of both the valence electrons and the chemical bonds in our molecules. So we're showing those valence electrons as dots, or as lines to indicate a bond. So a line equals a bond, and one bond represents two electrons shared by two electron elements. Okay? And the dots are, as they were before, just paired electrons that are not part of a chemical bond. So in this arrangement over here, we've got one oxygen and two hydrogens, right? We've got two electrons there and two electrons there. But in this bond, one essentially belongs to hydrogen, one belongs to oxygen. And same thing here, whereas these paired electrons here that are not part of a bond, those are exclusively oxygen. Okay? So we're going to go through how do we go about knowing where to put lines and where to put dots in our Lewis structures. And we're going to go through a few of those steps now. And we will add complexity to this over time. But we'll start with step one, which is to determine the total number of valence electrons in the entire molecule or polyatomic ion. Okay, so for example, methane and carbonate. So methane is a molecule, right? And it's a molecule composed of one carbon, right? Which would be 4 valence electrons, right? And that's what that information that we get from our periodic table, right? Carbon is in that column that has 4 valence electrons. Now, we're going to have 4 valence electrons plus 4 hydrogens, right? So each hydrogen contains 1 valence electron, so it's going to be 4 times the 1 valence electron that hydrogen has, right? So that's going to be essentially 4 plus 4, which would be a total of 8 valence electrons in the methane molecule. Again, that's 4 for the single carbon. Each hydrogen has 1, but we have 4 hydrogens, so it's going to be 4 times 1. So this is 4, there's 4, 4 plus 4 makes our 8. Now, slightly more complex is when we apply a charge to our molecule. Okay, so again, we've got a carbon atom there, which has 4 valence electrons. All right, we've got oxygen, which each oxygen contains 6 valence electrons. Okay, and we've got 3 of those. So if we go 4 times 1 plus 3 times 6, that's going to give us 18 plus 4, whoops, excuse me, that'll give us 22 valence electrons. Now, we have an associated charge there. Let me get a different color here, right? We have this little charge right there with that 2 minus, right? What that means is that carbonate molecule has 2 extra electrons associated with it. Okay, so we've got the 22 that come from the 1 carbon and the 3 oxygens, right? We've got an extra 2 valence electrons that come from that minus 2 charge, making a grand total of 24 valence electrons, right? Now, that step right there, being able to do step 1, calculate the total number of valence electrons in a molecule or polyatomic ion, is essential. We have to get this step right in order to correctly do our Lewis structures. Okay? So, you add up the total, so you look at the individual elements, multiply their number by the subscript, okay, which would be the 3 or the 4 there, right? Then, if there is a charge associated with it, we add or subtract electrons accordingly. So, for example, if I took ammonium, right, which is NH4, right, I'm going to have 5 for the nitrogen, and then 4 times 1, because each hydrogen has 1, that would be 9, right? But ammonium has a plus charge associated with it. So rather than adding an extra electron, I'm going to subtract 1 to make that 8. So a plus charge means subtract. A minus charge means you add extra electrons. I know that seems backwards, but that's because electrons are themselves negative. So you're either subtracting a negative or adding a negative, which means subtracting a negative means adding, adding a negative means subtracting, right? So, but again, this is a super, super important step, and we'll do a little review of this tomorrow when you guys come in, but I want this to be kind of in your notes in the first place. So you add the total number of valence electrons plus indicate any extra or deficient electrons we have to get a negative or a positive charge. Alright. Now, once you know the total number of valence electrons, you can then identify your central atom, right? So, first of all, central atom is never going to be hydrogen, right? It's usually the element with the smallest subscript, right? And it's usually going to have a lower electronegativity than its surrounding atoms. Okay? So, let's go back to our example, right? So we know hydrogen is never going to be our central atom, right? So we automatically know that in methane, carbon is going to be our central atom because hydrogen never is. Alright? Now, moving on though, in the next example here with carbonate, we have carbon and oxygen, so there's no hydrogen, so we can't use that rule. Alright? Now, we can probably apply either one of these next things to decide that carbon is going to be our central atom again here. Alright? So, first of all, carbon has no subscript, so we meet that. That'd be carbon. Likewise, if you look at your periodic table, carbon also has a lower electronegativity, which would mean that's probably going to be carbon. So, carbon ends up being our central atom in that molecule as well. So, in both of those, carbon is the central atom. We could tell in the first one because we know it's not hydrogen automatically, and in the second one because carbon has a lower subscript and it also has a lower electronegativity. Right? So that is how you identify your central atom. Now, we've got a total number of valence electrons, right? Which, as a reminder, is 8 here and 24 here. All right. We've then identified in both cases carbon is going to be our central atom, which, by the way, carbon is almost always going to be a central atom. All right. But we can use these rules here, or the little clues, to figure out which one it is. All right. We've done that. Now we're going to draw a skeleton structure. All right. So once the central atom has been identified, we'll place it in the center and draw enough lines to represent the bonds to the other elements. All right. So I'm going to go for methane here. So I'm going to go carbon in the center. I'm going to draw a line there, 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 and there. Right. So one line per subscript for the surrounding elements. Right. So there's a 4 there. So I get 4 lines around carbon. I'm going to go ahead and write an H there, an H there, H there, and an H there. That is my skeleton structure for methane. Alright, now for carbonate, I'm going to have a C in the center, right? But I'm only going to draw 1, 2, 3 lines because there's only 3 oxygens, and I'll put an O there, and an O there, and an O there. Now this, I will tell you right now, these are not complete yet, right? I have some other things I have to add, but this is just my skeleton. This is where I'm going to start my Lewis structure. I put my central atom in the middle. I draw enough lines to indicate a bond to each of my other elements that are a part of that molecule, right? So 4 lines for methane because there are 4 hydrogens. And I put a hydrogen after each line. 3 lines for carbonate because there are 3 oxygens. And I draw 1 line connecting each oxygen to the carbon in the center. Alright? So that's my skeleton structure. Moving forward then, now I have to go back and identify the remaining valence electrons and put them as dots around the surrounding elements, right? So I'm going to first add up to 6 to each surrounding elements. I'm going to never add dots to hydrogen, so I'm going to go back and just rewrite my skeleton structure. H, 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 and H. Excuse me. Fix that real quick. Alright, whoops. And for carbonate, I'm going to go C, O, O, and O. Right, so those are the skeleton structures I already drew. I already calculated this at 8 valence electrons and this one at 24. Alright, so first of all, one thing I want to make sure is clear. A line, a single line equals 2 valence electrons. Alright, so the first thing I'm going to do is I've got my lines in there. I'm going to count how many the lines represent. I've got 2, 4, 6, 8. Right? I already have all 8 valence electrons in there. Likewise, I'm never going to add any valence electrons to hydrogen because it only ends up with 2 every time. So no dots on hydrogen, please. No dots to hydrogen. Now, going down here though, I've got 3 lines represented. Right? So I've got 2, 4, 6 valence electrons. I've got to assign all 24 of those in, right? So I'm going to begin by adding up to 6 more to each of my surrounding elements. Alright? So I've got 2 there. 4, whoops, fix that. What just happened? 4, 2, so there's my 6 more, so that makes a total of 8 around that oxygen. 2, 1, 2, 3, 4, 5, 6, right? That makes it 8 more, so now I'm showing 8 plus 8 is 16, and there's number 8, 17 and 18 in this line, alright? And then 1, 2, 3, 4, 5, 6 there, alright? So let's count my total number of valence electrons around carbonate. I've got 8 here, plus, I'm just going to draw a little 8 there, 8 more, and 8 there. So I'm showing all 24 valence electrons. Okay, I don't have any leftovers to put onto my central atom in this case, right? Now, if, let's say I had 2 extras that needed to be put in there, I would then put dots like there and there, like that. But I don't have any leftovers, so I don't need to do that. Alright, so let's do one example where we do have to do that. Let's take ammonia, NH3, right? So I've got 5, whoops, excuse me again, 6, 7, and 3. That makes 8 valence electrons, right? Hydrogen is never my central atom. That means nitrogen is. So I'm going to go N, H, H, and H, right? I can't put any dots around my hydrogen. So I've got 2, 4, 6. I need to put 8 in there. So I have 2 left over. Those would go there like that for ammonia. Alright, so that's what that little, whoops, man, my computer's acting up on me. So when I say only leftovers go to the central atom, that's after you put as many as you can, right, around your surrounding atoms. If there's still more electrons to assign, then those go on that central atom. Alright, but because we can't put dots on hydrogen, no dots on hydrogen, please, right? I had 2 left over after the 2, 4, 6. I needed to assign 2 more. Those went there. Okay? So, now, we're still not done. We've added our remaining valence electrons. Alright? Put the dots where they go. Now, there's one more step that we have to consider here to make sure that our Lewis structure is complete. And that involves, right, making sure we have our 8 valence electrons, right? That octet thing that we talked about on a few different occasions back in last unit and the beginning of this one. Alright? So we have to make sure that our central, so we got an octet around all the atoms that are supposed to have an octet, which again would not include hydrogen. Alright? So if we go back, if I draw my methane, I got C, H, 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 and H, right? I've got 2, 4, 6, 8. That one's done, right? My carbon there, each line is 2 valence electrons. 2, 4, 6, 8, 4 lines times 2, 8 valence electrons. So my methane molecule is good to go there, right? I've got all the electrons assigned. I've got an octet for my central atom. My hydrogens get there too that they want to be like helium. That one's all set. Now with my carbonate though, if you guys will recall, I had a C connected to an oxygen with 1, 2, 3, 4, 5, 6. Another oxygen. 1, 2, 3, 4, 5, 6. And another oxygen. 1, 2, 3, 4, 5, 6. Okay? Now, that gives me an octet for my oxygens, right? 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But my carbon does not have an octet. It only has 2, 4, 6. Alright? If my central atom does not have the octet, I'm going to create what's called a double bond using the paired electrons from an outer element. So, in this case, it does not matter which oxygen I choose, right? But what I'm going to do is I'm going to take one of these pairs from this guy. I'll just choose that one, for example, right? I'm going to erase them. And rather than putting 2 dots, I'm going to draw a second bond there. Alright? And so what that's going to show is that one of my oxygens creates a double bond with my central atom, while the others are only a single bond. And again, it wouldn't matter which oxygen I chose in this case. Alright? We're going to talk about what actually occurs with what are called resonance structures later. But it doesn't matter which oxygen to choose. Right? If I don't have an octet around my central atom, I need to correct that by creating a double bond. Now, I cannot create a double bond with hydrogen. That's not going to work. But any other surrounding element I can. Alright? Now, this oxygen has 8. This oxygen has 8. This oxygen has 8. And the carbon has 1, 2, 3, 4 lines around it now. Satisfied its octet. And check. We are done. Alright? So, hopefully when you guys walk in the door tomorrow, you talk about an octet. I can talk about step 1, 2, 3, and 4. And we can do a second repetition of this information, and you guys will be all good to go. Peace!